Before I even start the lecture, I want to make it clear that degeneracy factor is not particularly related to degenerate semiconductors, as degeneracy factor can also be present in non-degenerate semiconductors. We started our study with intrinsic semiconductors, then we discussed Fermi direct polarity function, which shows the distribution of electrons at different energy levels even between conduction band and valence band, though there are no available quantum states, or in other words, we do not have any stable quantum states between conduction band and valence band. But when we dope an intrinsic semiconductor with an impurity, we actually introduce another stable quantum state which exists at dopant energy, which actually slightly changes the distribution of electrons between different energy levels in the semiconductor. We will study for N-type and P-type semiconductors simultaneously. The polarity function of electrons occupying the donor state is here small nd is representing number of electrons at donor energy levels, whereas capital ND represents doping concentration of N-type impurity, and G is degeneracy factor. Now you have to understand that degeneracy factor for N-type impurity is totally responsible due to the spin of electrons, as the electron can have spin up or spin down polarity at the donor energy level. Therefore, an electron can have two possibilities to be present at donor energy level. Each donor level has two possible spin orientations for a donor electron. Thus, each donor level has two quantum states. However, by adding one electron, the vacancy requirement of the atom is actually satisfied, so that the second electron cannot be further added at the same donor energy level. And since there are two possibilities of spin, which is spin up or spin down, therefore for N-type extrinsic semiconductors, G is generally equal to 2. Similar formula exists for hole concentration at acceptor energy level. Here, Pa represents density of holes at acceptor energy level, and Na represents doping concentration of P-type impurity, and G is the degeneracy factor. Now, there are slight differences between the degeneracy factor which is present in P-type semiconductors compared to N-type semiconductors. The thing is, here the degeneracy factor can be equal to 2, 4 or 6. But why is it so? The reason is that the actual band diagram of common semiconductors like silicon and gallium arsenide exist like this. This is conduction band, this is heavy hole band, this is light hole band, and this is split of hole band. And assume that here we have acceptor energy level. So degeneracy factor G can be written as 2. 2 here represents spin up or spin down polarity multiplied by 1, 2, 3. It means that it may be possible that the hole which is coming from the valence band to occupy the place in the acceptor energy level, it may be from light hole or heavy hole band, or it may be from split of hole band. So there are two possibilities of spin up or spin down, which are further multiplied by the possibilities of the origin of the hole. But this degeneracy factor is dependent upon the material, meaning that it may be possible that the split of hole band is quite far from the acceptor energy level that the hole cannot move to the acceptor energy level. The degeneracy factor G for silicon and gallium arsenide is equal to 4. We consider heavy hole and light hole band here. One more important point is assume that we have conduction band and we have donor energy level. Now another expression which can be written for the density of electrons present at donor energy level is Nd, which is equal to Nd minus Nd plus. What does this mean? It means that if the doping concentration is Nd, then Nd plus represents the concentration of impurity atoms which are ionized, and smaller Nd represents remaining number of electrons which are actually present at donor energy level. We know that there is only one possible stable state in the energy band gap, which is ED. Now, if there is doping concentration Nd, then obviously there are two possibilities. All the impurity atoms are initially present at this energy level. Now, if they have absorbed sufficient energy, then they will go up to conduction band, and the concentration of impurity atoms which have absorbed sufficient energy is Nd plus, and the number of impurities which are still present at donor energy level is Nd. So obviously doping concentration is equal to concentration of electrons in the conduction band plus concentration of electrons at the donor energy level, and after rearranging it we will get Nd is equal to Nd minus Nd plus. Similarly, we can also write for p-type semiconductor, which is Pa is equal to Na minus Na negative. The most important point in this lecture is to remember the fact that degeneracy factor can be different for p-type and n-type semiconductor, and remember the value of degeneracy factor for p-type impurity for silicon and gallium arsenide, which is equal to 4. Now we will solve a related question. A non-degenerate n-type semiconductor has 5% neutral dopant atoms. Its Fermi energy level is located at 0.25 electron volt below the conduction band, and the donor energy level has a degeneracy of 2. Assuming the thermal voltage to be 20 millivolt, the difference between EC and ED is. This was the question which was asked in GATE 2024 for 2 marks. Now it is said that neutral dopant atoms is 5%. Neutral means Nd. As I just told you that Nd is equal to Nd plus Nd. This is the doping concentration. This is the concentration of impurities that are ionized, and this is the concentration which is present at neutral state or which have not absorbed energy sufficient enough to move to the conduction band or to get ionized. So we can say that smaller Nd is 0.05 of Nd. Now we put these values in the equation we just discussed about. You know that the value of degeneracy factor is given to be equal to 2. thermal voltage, which is kT by Q, is given to be equal to 20 millivolt, and we can find the value of kT to be equal to 20 milli electron volt. Therefore, ED minus EF will be equal to 20 natural logarithm 38 milli electron volt. After calculating, we will get the value of ED minus EF to be approximately equal to 0.073 electron volt. Now it is also given that Fermi level is located 0.25 electron volt below the conduction band, meaning EC minus EF is equal to 0.25 electron volt. This can also be rearranged as now this expression we just found to be equal to 0.073 electron volt. EC minus ED plus 0.073 electron volt is equal to 0.25 electron volt. It gives the value of EC minus ED to be equal to 0.25 minus 0.073 electron volt. The final value of EC minus ED comes out to be around 0.177 electron volt, which is the final answer. The acceptable range provided for the answer was 0.17 to 0.19. Probably it was the first time that a question from degeneracy factor was asked.